Okay, let's get started. So we've been talking about Bayes nets, which are representations of probabilistic models over a domain of variables. And in particular, we've been talking about how to answer questions about various quantities, queries given evidence, and how to do that in as efficient way as possible. Today we're going to talk about an entirely new kind of approach for doing inference in Bayes nets, which involves sampling. So, mostly, we're going to take a huge step back, forget everything we know about variable elimination, everything we know about actually constructing joint distributions, and instead talk about a completely different way to do inference in the distribution represented by a Bayes net. So let's remember what a Bayes net actually represents. So it's a representation of a probabilistic model over some domain of variables. You have a directed acyclic graph. You have one node per random variable. And living inside each node is a conditional probability that specifies the probability of all the outcomes of that node given an assignment to the parents. This encodes a joint distribution. And we've seen this before a bunch of times in recent lectures, but today we're really going to need to remember what things you have to multiply together to actually get the probability of an event in this joint distribution. So a Bayes net explicitly it's a bunch of little local conditional probabilities, and implicitly it encodes a joint distribution over all those variables that's given by the following formula. So if you give me a complete assignment to all the variables x1 through xn, the probability under the Bayes net is the product of all the conditional probabilities for each of those x sub I given the parents. Now, where do these all come from? Each node of the Bayes net representing a variable has those tables buried in it. Okay. What we wanted to do with Bayes nets was answer questions like, hey, what's the probability of this variable given some pieces of evidence we observe? What's the probability of this disease given these tests? What's the probability that my battery is dead given that this light is blinking in my car? What's the probability of this insurance, parameter or whatever it is given the known quantities? And for large Bayes nets, it wasn't practical to construct the whole joint distribution because it's exponentially large. And even if you had it sitting there in memory, it wouldn't be practical to answer queries because most queries involve a small number of variables, which means you would have to sum out over all the various combinations of settings of the other variables, and that would take exponential time. So we had this algorithm, variable elimination, which involved alternating between inflating little bits of the Bayes net and summing out variables you don't want, where we sum things out aggressively before the factors that we build have a chance to get exponentially large. How big do they get? Well, in general, if there are d elements in the domain and there are k variables in a factor, you're going to have factors of size d to the k. That means k can't get too big. What happens in an arbitrary Bayes net? Sometimes there aren't any orderings that are going to give you only small factors, and it can still be very expensive. The ordering can matter a lot. We saw cases where there were networks that had good orderings and bad orderings. There's also networks that only have good orderings, and there's also networks that have no good orderings. Sometimes there's a good ordering and a bad ordering, but it's really hard to find the good ones. But in general, variable elimination was better than inference by enumeration, even though in worst case, everything was exponential in the size of the Bayes net, and we saw why that sort of has to be, because Bayes nets can compactly encode satisfiability instances. So we have this algorithm, variable elimination, which basically is going to add a ton of entries of the joint distribution together in a hopefully efficient way by kind of moving some of the sums in the expression, but it might still be slow. Today we're going to do something entirely different. Today we're going to do an algorithm that's really, really fast, but the answer might be totally wrong. And this is different than how we normally approach problems in this class. Normally we have an exact answer, and we're going to find it. And we're going to try to make it as efficient as possible, either in a way that we can show the worst case computational complexity isn't too bad, or maybe the worst case complexity is bad, but it's still in practice feasible for lots of problems. Today we're going to talk about sampling-based methods, which you can run them as quickly as you want. But if you don't run them long enough, your answer may not be very accurate. And so here there's a trade-off between compute and accuracy, and that's not the normal trade-off we have. So what is sampling? There's actually two entirely different reasons you might sample. So sample is a lot like doing repeated simulation. In fact, we've already done some sampling in this class. We did sampling when we did reinforcement learning, where we were like, hey, what's the value of this state? Or what does this action do? And so we'd try it. And then we tried again, and we tried again, and again, and again, and again. And if we tried it enough times, those probabilities would start to converge to the right values. That use of sampling is learning. So in that case, you don't actually know the distribution. Like, we didn't know the distribution of the slot machine, and we had to keep playing the slot machine so that we could learn how often it pays off. So that's a case of learning. You don't know the various probabilities, but you're going to interact with the real world to discover them. That's learning. We're going to use sampling today for a very different purpose, which in a lot of ways is a little counterintuitive. Today we're going to use it for inference. And that means we're going to go to our BaseNet, in which we know all the probabilities. How did we get them? Maybe they were handed to us. Maybe we actually got them from learning. But right now there's a BaseNet right in front of us. And it tells us that the probability of this variable, given the settings of these other variables, is 0.37. Okay, so we actually know all the probabilities, but we're going to sample anyway. When you sample in a network that you already know, it looks like simulation. You walk along the network and you say, well, if this happened, let's see what would happen at this variable. And you flip some coins, and you get a sample out that is a sort of probabilistic simulation. And in this case, the reason you're getting a sample is not because you don't actually know or are not able to compute the underlying probabilities. It's because sampling turns out to be faster than computing the right answer through brute force. So here's the basic idea in sampling, regardless of whether you're doing it for learning purposes or for speed purposes. The basic idea is we're going to draw n samples, where n might be very large, from some sampling distribution S. And we get to define the sampling distribution. We'll see several different examples today of different sampling distributions that are given by the different algorithms we're going to cover for sampling. But there's some sampling distribution that hopefully we can characterize. You're going to draw n samples from that. Inside those samples, which are all events that look like outcomes of S, and you're going to compute an approximate posterior probability. Whatever query you're trying to answer, you'll compute it over your samples. And that's efficient because it scales in terms of time with the number of samples you take. If you want it to be more accurate, you take more samples. And now you might think can't be really a free lunch there. There's got to be some trade-off between accuracy and time. And if I have a really tricky distribution, maybe some queries need a lot of samples in order to get accurate. There are going to be trade-offs like that. But you can always stop it and get the wrong answer. What you want to show is that as n grows, as n goes to infinity, this procedure is going to converge to the true probability you actually wanted to compute. And so every time we introduce a sampling algorithm, we need to sort of argue that if I draw a bunch of samples from this, I'll actually get the right answer. Even though, of course, if I draw a small number of samples, it's the luck of the draw. All right, so we're going to have an atomic building block when we do sampling. And that is we need to be able to sample from big distributions in BaseNets. And there's going to be algorithms for that, where you walk along the network going variable by variable in an appropriate way. But before we can do that, we need to understand how to sample from a single multinomial distribution. So let's say, for example, we have this distribution here. There's a random variable C. It's a color. It's red, green, or blue. And I have right in front of me the probabilities. Now remember, I'm not doing learning. I know the probabilities. I know that red happens 60% of the time. But I'm going to draw a sample from this distribution. So I'm going to flip some kind of coin, and I'm going to basically flip conceptually I'm going to flip a three-sided coin that says red, green, and blue, where the red side comes up 60% of the time and the green side comes up 10% of the time and so on. But how am I going to get this coin? How am I going to actually get this single sample? Well, what I'm going to do is I'm going to manufacture a sample over this distribution from a primitive sampling distribution over, say, the real interval from 0 to 1. So for example, if you call random, you'll get a uniformly distributed number between 0 and 1. And then step 2 is to take that sample over the 0-1 interval and convert it into a sample over the event space for C. How do we do that? We divide up that real line into sub-intervals where the size of each sub-interval is equal to the probability of the outcome. So for example, I might grab my number between 0 and 1 and say, well, if it's between 0 and 0.6, I'll call that an instance of red. And if it's between 0.6 and 0.7, I'll call that an instance of green. And if it's between 0.7 and 0.1, I'll call that an instance of blue. Okay? So I could do that. Let's say my call to random returns 0.83. I would look and I would say, well, that's not in the first bucket, that's not in the second bucket, that's in the third bucket, so I'm going to say I just sampled the value blue. Now, why would I ever want to do that? I could draw a bunch of samples. If I sampled 8 times, I might get 5 reds, 2 blues, and 1 green. Do those seem plausible given these probabilities? They're plausible. Why would I ever want to do this? Well, I basically wouldn't, right? I already know the probability of red. Drawing 10 samples, and this time I got 7 instead of 6, that's really just introducing variance into the process. So for this one-dimensional single variable, I wouldn't actually have much use for sampling from this known distribution. However, in a Bayes net, there is a use for sampling from the entire network, because listing all the outcomes is too expensive, even if I can create them given infinite time. All right. So here's what we're going to do today now that we have this building block of being able to sample from any given single multinomial distribution. So we'll think of that as a primitive now. We're going to look at 4 different algorithms for drawing samples and think about what they do and what we can understand about them. Yes, questions before we start? Wow. It's the first time I've ever been asked to turn my mic up. How's that? All right. Any other questions? Any other volume requests? Okay, so we're going to do some prior sampling. So I like to think of samples as snapshots, assignments to random variables that come across a conveyor belt. And in the prior sampling algorithm, we're just going to draw samples from the distribution of interest. So this is the basic building block. Here's a little Bayes net. This is a Bayes net that says half the time the sky is cloudy. That's P of C. And then there's a sprinkler on my lawn, and there's a dependence between the cloudy and the sprinkler. So what does this look like? If it's cloudy, the sprinkler is usually off. If it's not cloudy, half the time the sprinkler is on. There's also a dependence between cloudy and rain. So when it's cloudy, it usually rains, and when it's not cloudy, it usually doesn't. And then, in addition to sometimes it's cloudy, sometimes there's a sprinkler on, and sometimes there's a rain, sometimes my grass is wet. Okay. So how does that work? Basically, the sprinkler can make my grass wet, and so can the rain, and so there's a conditional probability table here that describes how W responds to S and R that basically says if it's either S or R, then it's probably wet grass. But if there's neither rain nor sprinkler, there's probably not wet grass. Okay, so everybody get that Bayes net in your head because we're going to use this Bayes net over and over again. It's an interesting Bayes net because the variables sort of separate, but then they come back together at the bottom. So if I look at this, what can I do? What do I know how to do with this Bayes net? Given time, I know how to create the whole joint distribution. So I could do that right now. I could ask you, hey, what's the probability that it's cloudy, there's a sprinkler, it's rainy, but the grass is dry? We could compute that right now by multiplying a bunch of conditional probabilities together. We're going to do something similar to that. Instead of computing an entry of the joint distribution, we are going to create an event, which is an assignment to these 4 variables. But we're going to create it by walking along the Bayes net. So we'll go to cloudy, and we'll say, well, sometimes it's cloudy and sometimes it's not. My samples will come out both ways. Right now, it's time to pick a single sample. So I'm going to flip a coin, and here it's going to be a 50-50 coin, and maybe it turns out it's plus cloudy. So green here will be plus and red will be minus. All right, time to go to the next variable, because I don't have a complete assignment yet. So I'll go to the sprinkler. I've already picked plus C, so now I'm going to pick a value for S. It's probably going to be minus S, but there's a 10% chance that when I flip this 90-10 coin, it'll come out plus S. So let's flip the coin. Okay, it came out minus. I go to the next variable, rain, and it looks like I have an 80% chance of getting a sample of plus R and a 20% chance of minus R. Comes out plus R. And then I go down here to the wet grass. There's no sprinkler, but there is a rain, and so the probability of wet grass is 90%. I flip another 90% coin, and I get plus wet grass. So I walked along this network. If I did this again, and I flipped those coins again at each node, Next time, I'm presumably going to get a different sample, and then a different sample, and then a different sample. Each time I get a sample, I write it down. Okay, so my first sample was plus C minus S plus R plus W. And I can do that again and again and again. I can draw as many samples as I want. We could ask some questions like, okay, that first sample, how often is that going to happen? I mean, will it always come out that way? Certainly not. What's the probability that I will get the sample plus C minus S plus R plus W? Well, the probability that I'm going to get the plus C part, that's going to be true of half the samples. And then of those samples where I got a plus C, the probability that I'm going to get a minus S, that's going to be true of 90% of those samples. And then when I go to plus R, it's going to be 80% of the samples and then 90% of the samples. And if I multiply those together, I can determine the probability of the sample, which is just the probability of this event in the distribution described by the Bayes net. So when I draw samples according to this procedure of walking node by node and just flipping the coin the way it says in that node, I end up with samples coming out in a way that exactly matches the probabilities in the joint distribution. Okay? Does that make sense? You might wonder, why the heck would I do this? Right? Because I can compute those probabilities, but that is the probability of each sample type. So here's the prior sampling algorithm. If you're going to draw n samples, you can draw as many samples as you want. For each sample, you do the following. You visit each node, sampling a value for that node given the parents. And so you say, what happens if I visit a node before a parent? You can't do that, right? So you have to do this in a topological ordering of this, where you don't sample something until all its parents are sampled. How do I know there's such an order? It's an acyclic graph. Okay. After you sampled all the nodes, you return it. That's your sample. How many samples do you want to draw? That's up to you. So we already talked about this process generating samples with a certain probability. So let's parse this expression. This is a sampling distribution. S is a sampling distribution. It's like P, except when I write it down, I might or not actually be a probability. But here, S is a sampling distribution. It's for PS is prior sampling. And the probability that I'll get the sequence x1 through xn as the assignment from this sample, the probability I'll get that snapshot is the product of the probability of each piece given its parents. And that, as we said, is just the probability of that same exact event under the joint distribution. So we found a way of drawing events from the full joint distribution with probability P that's not too hard. So what do we know? Let's say we take some event like x1 through n, and we draw some samples. We might not get any samples of that event. We might get a lot. Let n be the number of samples you get of a certain event. One thing that should seem very plausible is that as n goes to infinity, the fraction of samples that come out as that event compared to the number of samples you take, that's the sampling probability, which we know from the form of the sampling process is going to be the probability in the network. What this means is the sampling procedure is called consistent. You may have noticed that in every unit, we use the word consistent, and it always means something different. This is what consistency means here. Okay? So we say a sampling procedure is consistent if the ratio of the samples in the limit goes towards the actual distribution that we're trying to sample from. And you might look at this and be like, well, how could it be inconsistent? Well, here's an inconsistent sampling procedure. What if I just went and I picked each node 50-50 independently? I would still get samples. They just wouldn't kind of come out according to a distribution that had anything to do with the one I'm trying to model. All right, let's do some prior sampling. So here's this little network. We run that procedure where we visit each node and out pops sample 1, and then out pops sample 2, and sample 3, and sample 4, and sample 5. We've got 5 samples. Now normally we would have like maybe millions of samples. We got 5. What can we do with these samples? Well, with these samples represent a distribution. And we can do anything we would do with an actual distribution, we can do with these samples using counts instead of probabilities. So let's say I would like to know in this Bayes net, which remember, like deep down, this represents a joint distribution over C, S, R, and W. And I could do things like I could compute in this network, I could compute the probability of W. How would I do that? Variable elimination. So you say, I hate variable elimination. I haven't reviewed those lecture slides yet. I'm not going to do that. How else could I do it? Well, I could look in these samples. And I could say, well, in these samples, sometimes W comes out plus and sometimes it comes out minus. And in these samples, what's the probability of plus W? It's 4/5 or 80%. So I could write in these samples, I could write the probability that W is plus W is 0.8. Great. Do you think that's actually the probability in the network? I mean, I have no idea, but probably not, right? This is just an empirical probability of this quantity of interest, not computed in the network, but computed over samples which were drawn consistently with the network. So if instead of 5 samples I had 5 billion, this 0.8 would be about right. As it is, hey, it's a number. Okay, so we get counts, and we can normalize any events over those counts to get the probability of that event under our samples. This approaches the true distribution if we have more samples, and we can estimate anything else that we like. So let's do some practice. Can we compute the conditional probability over the variable C given that the grass is wet? So how likely is it to be cloudy given that the grass is wet? Let's do it. All right. Well, when I look at these samples, I say, I care about the case where the grass is wet. So this sample here, this sample doesn't do much for me because the grass is not wet there. So I look at the other 4 samples and I say, how often is C true? Looks like 3 out of 4. So there's my answer, 3/4. Is it right? Probably not. All right. Probability of cloudy given rainy and wet grass. Man. Okay. Probability of cloudy given rainy and wet grass. All right. That one's not rainy and wet grass. That one's not rainy and wet grass. So of the rainy wet grass samples, of which there are 3, how often is it cloudy? All the time. In all those samples it was cloudy. Now, in this network, is the probability of cloudy given plus R plus W 1? Probably not. But if I drew enough samples, this would start to approach the correct probability. Here's an interesting case. What's the probability of cloudy given minus R and minus W? So I look through my samples, and I say, how many samples do I have for this condition, minus R minus W? Uh-oh, I have no samples for that. So I can't even answer this question yet. And this is a real problem, because in prior sampling, I just sort of pull samples off according to the distribution. Sometimes they match my evidence, sometimes they don't. And if I have a question about some variable like C, conditioned on some rare evidence, I just got to keep pulling samples off the conveyor belt until I get some that match my evidence. I might never get any that match the evidence if it's rare enough. So that's a real problem with the sampling method. Okay, but it's fast. We can stop at any time. And, of course, the drawback is that it may be very inaccurate. Okay. Any questions on prior sampling? Yep. What do you do if you never get the evidence? So, in general, you want to set up your sampling procedure so that you're seeing the conditioning environment. You're seeing the evidence. And if your evidence is very rare, prior sampling, or actually in this case rejection sampling, it's going to turn out as what we were doing there, is a very poor algorithm. So you've got 2 choices. You can run for a long time, or you can have a better sampling algorithm. I mean, you could make a decision about, like, in your code, if there is ever a 0 in the denominator, you have to do something reasonable. But the bottom line is any choice you make is going to be a sort of it's going to be an engineering level fix. Mathematically, you just don't know very much. Okay, so let's talk about rejection sampling. So the metaphor of prior sampling is events are coming off the conveyor belt distributed according to the joint probability that we have in our domain. And as they come off, we tally things up. In rejection sampling, we go into the sampling procedure with some condition that we care about, like plus R plus S or something like that. And so, as the samples come off our conveyor belt, we take a look at them. And if they're samples we can use, meaning they match our evidence, we keep them. And if they're samples we can't use, we reject them. We actually sort of already did that when we computed some of those queries on the last slide, where we were crossing things out saying these samples don't represent my data condition, so they're not relevant to this query. So in rejection sampling, samples come off and you reject them if they don't match the evidence. So let's look at the difference. If we'd like to know, say, in this network here, we'd like to know the marginal probability of C. In fact, it's sitting there in the network, so we wouldn't have to compute anything at all. But let's just say we did it with sampling. Okay, we could do prior sampling. We would get samples like this. We don't actually have to keep the samples around. We could tally for each sample as we draw it. We could be like, oh, you're a plus C sample. You're another plus C sample. You're a minus C sample. You're a plus C sample. And we can keep tallies of the event we care about as the samples stream by. In the end, we would normalize to get a probability. We could then discard the samples. And they're gone. We don't need them anymore. Whoops. If we want to know what's the probability of cloudy given that there's a sprinkler out, you can do the same thing. These samples come by, and you tally how many come up plus C versus minus C, because that's your query variable of interest. The difference is, everything that comes off the conveyor belt that doesn't match plus S, you just throw it in the bin. You don't tally anything, because that's not relevant to your data condition. This is called rejection sampling. And this is consistent for conditional probabilities. It's the exact same argument as why prior sampling is consistent with the entire distribution. Okay. So from these samples, we can answer any question. We could say, what's the probability of plus S given plus C? And we'd be like, okay, that's this sample, and this sample are plus C. I would discard the rest as they pass. And as I go, I would say, okay, there's a vote for minus S, a vote for plus S, and a vote for minus S. And I would say minus S 2/3, plus S 1/3. Okay, that's rejection sampling. Okay. Here's the algorithm, though we've now done it twice. Your input to this algorithm is the evidence that you have instantiated. So I know the values of this test and this test, or this light in my car is blinking. So I know the evidence. Then I go through the network, variable by variable, and I sample values for that variable. If they happen to come up in a way that matches my evidence, great, I return the sample. And if they don't, I just reject the sample, and I start on a new sample. Okay, so let's think about what that means. That means we're walking through the network, we get to the evidence variable, and there's this moment where I'm wondering, is it going to come up in a way that matches my evidence or not? And that moment determines whether or not we throw out the sample or keep it. Okay. Remember, the problem is we might end up throwing out a lot of evidence. So we're going to go back to that moment when we weren't sure whether or not the random variable that matches the evidence would come up in a way that matched the evidence. We're going to fix that. We're going to fix that by doing something called likelihood weighting. So if we look at the caricature here, if you imagine that your evidence is you know that the shape coming off the conveyor belt is blue, and you want to know what's the distribution over shape given color blue, we're going to take every blue thing that comes off and throw it into one of the shape bins, and that's going to be our distribution. So let me just write that down. Whoops. Let me just write that down. So we're trying to compute the probability distribution over shape. Okay, I just changed models here. We're not in the sprinkler anymore. Probability distribution over shape, given that C equals blue. So what do we do? Colored shapes come off the conveyor belt, and if it's blue, we throw it into one of the shape bins. This one's going in this bin. They go into the bins. In the end, I'm going to count up how many things fell into each bin. When I get something that's red, it doesn't match my evidence of blueness, so I throw it out. In likelihood weighting, we don't have the problem of throwing out samples because we make them all blue. That is, when we're drawing samples from the network, we don't risk the sample not matching the evidence at the evidence nodes. We fix it to equal the evidence at the evidence nodes. So there's a big plus. We don't have to throw out any samples. Every shape comes out blue. But there's a problem. What's the problem? Let's go see if we can see the problem. Okay, so the problem with rejection sampling, if your evidence is unlikely, you reject lots of samples. Actually, how many do you reject? So let's say we're trying to compute some query, P of Q, given some evidence variables E. So you have a bunch of evidence variables E. So I'm getting samples out of my Bayes net using prior sampling, rejection sampling. Each sample pops off and I look at it and I say, do you match my evidence E? Nope, I throw it out. Do you match my evidence E? Nope, I throw it out. Do you match? Yes, I'll keep this sample. What if your evidence is like this test result and this test result and this test result and this test result? How many samples am I going to keep? I'm only going to keep the ones that pop off the conveyor belt, miraculously matching all my evidence variables. What fraction of samples from the full distribution match my evidence? Well, P of E. Right? That evidence has some probability, and I'm drawing things from the network according to the distribution of the full joint, and so things come out matching my evidence with P of E. Well, if my evidence probability is 0.3, that means I keep 30% of my samples. If my evidence probability is 1 in a billion, it means I only keep 1 in a billion of the samples. And that's super inefficient because I spend all my time rejecting everything. And that's what's going to happen because your evidence is like some weird things you've observed. Next time you do it, you're going to observe some other weird things. So the marginal probability of your evidence is almost always pretty small. And that means with rejection sampling, you're almost always rejecting almost everything. So that's not great. And in particular, as you sample, you're not exploiting the fact that you know the evidence. You sort of draw your sample and then you're like, oh man, it didn't come up like the evidence. Oh, it didn't come up like the evidence again. It's like, well, you actually know the evidence. Maybe we should work this into the process. Okay, so we already did this, but here's an illustration. If I want to know the probability of shape given blue, and I draw all of these samples off the conveyor belt, I throw out everything except that one blue sphere, because it didn't happen to come across blue. So, here's the idea. We're going to rig the system. We're going to fix all the evidence variables as we walk through the network, and we're not going to sample their values. We're just going to fix them to the evidence. And that means that the sample distribution can't be consistent anymore, because suddenly everything is coming off blue. And if everything comes off the conveyor belt matching our evidence, it's not the same distribution. I mean, if nothing else, the probability of evidence used to be P of E, and now it's what? Now it's 1. Everything matches the evidence. So we've broken something. Let's go dig into the algorithm and see what we can fix what we're broken. But there's going to be a solution, which is to say that each of these samples that comes off is going to have a weight. And we'll figure out what that weight is. It's going to correspond to the probability of the evidence. And what that means is we're now going to go through and we're going to pull things off the conveyor belt, and they're all going to be blue. And so everything comes off blue. But they're not all going to come off with the same weight. And in particular, samples where it probably wouldn't have matched the evidence are going to come off with a very small weight. And samples where actually plausibly it could have matched the evidence, they're going to come off with a larger weight. Okay, so let's do an instance of likelihood weighting. Okay, so here's my network. What I did before is I started at the top and I sampled each node. And sometimes things came off as plus sprinkler plus wet grass, and sometimes they didn't. But now, every day is a sprinkler wet grass day. So let's draw a sample. I go to node C, and with probability 0.5, I'm going to get plus cloudy. I get plus cloudy. Okay, now I go to R, and with probability, let's see, it's plus cloudy, so with probability 0.8, I'm going to get plus R here, and with probability 0.2, I'm going to get minus R. No, we're not doing that one yet. Okay, so we have plus C. We're going to go to the sprinkler. Now, given that this sample has cloudy, what I would normally do is flip a coin at sprinkler, and it would come up as plus S 10% of the time, and it would come out red, minus S, 90% of the time. So, right here, imagine I haven't actually flipped the coin yet. Chances are I'm going to get minus S. I'm going to get a red node here. But my evidence says green. Okay, so what happens? I'm going to stop. There's this moment where I don't know what's going to happen in prior sampling or rejection sampling, and I don't know what's going to happen. But I know that if I got to this point again and again and again, how likely would I be to get the evidence of plus S? Well, basically 10% of the time that I get to this point, the next node that I sample, when I sample sprinkler, it will come out matching the evidence. So for every 10 samples that get here, 9 of them are going to get rejected. But 1 will survive. And that means, sort of, if you imagine we split into some, multiverse of parallel execution here, instead of flipping the coin and risking a 90% chance of getting minus sprinkler, I'm going to take the universes where I actually get plus S, and I'm going to pretend I'm going into those universes, which means this sample only really represents 10% of the samples that make it to this point. So when I go through, I'm going to multiply in, I'm going to rig this node, and every time I rig a node, I'm going to multiply the weight of a sample that begins at 1 by the probability that the thing that I rigged would have actually happened. All right, so now I go over to rain, and I say, well, this isn't evidence, so I'm just going to flip a coin and see where it falls. Maybe it'll be plus R, maybe it'll be minus R. It's plus R. Okay. Now I get to wet grass again. And when I get to wet grass, I look here and I say, I could flip a coin and see whether I get plus or minus W. But instead, I'm just going to fix it to plus W because I'm imagining that's my evidence. But not every single time I get to this point would it come up my way. But it would 99% of the time. And so this sample is going to get another weight of 0.99. And so what's going to pop off here is that you'll get samples, and they'll have weights on them. And why do these samples have weights? These samples have weights because the nodes that I rigged only had a small probability of actually having the chips fall the way I needed them to. And that probability needs to be captured somewhere, and that's captured in the weight of the sample. So here's the algorithm for likelihood weighting, and then we'll look at its properties. The input, again, just like rejection sampling, is the instantiation of your evidence. But now instead of rejecting samples that don't match the evidence, instead what I'm going to do now is I'm going to rig every sample to match my evidence. So I'm going to go along node to node, and if it's not an evidence node, I'm going to flip a coin according to the probabilities based on the parents, and I'm going to take whatever comes out. But when I get to an evidence variable, so that's the normal thing. When I get to an evidence variable, I am going to assign the value in my evidence to that node, and I'm going to multiply the probability of that actually having happened in an organic way into the weight of the sample. Okay? What comes off now is a sample that has a weight attached to it. And so you can imagine I pull this red ball, I pull a blue pyramid off of the conveyor belt, except it's now got the number 0.7 attached to it. And not every sample is going to have the same weight. Indeed, samples often have very, very low weight because you forced a lot of evidence nodes to be something that they probably wouldn't have been. And the weights on the evidence are, in general, very small. Okay, so that's likelihood weighting. Likelihood weighting, we take our network, we start at the top. We flip a coin for non-evidence variables, and we see it lands however it is. As a result, if I draw a sample from a Bayes net in which some nodes were actually sampled, and they took on whatever value the random number came up, and other nodes are rigged, what's the probability that I'm going to get, whatever, plus C, plus S, plus R, plus W? What's the probability that's going to happen? Well, the probability that I'm going to get plus C is P of plus C. The probability that I'm going to get whatever R is R given C. And so the sampling probability, the probability that we're going to get this sample, which includes my evidence every time, is going to be a product of the probability of the nodes that I actually did sample. But unlike before, there are not terms in this product for the nodes that I didn't sample. The nodes that I just rigged values to match the evidence, those conditional probabilities are not part of this product. And if I want probabilities to match my joint distribution, I have to have every single term one for each variable. However, samples have weights, and the weight on a sample for Z sampled variables and E fixed evidence variables, the weight on a sample is all the other terms of the joint probability. It's the probability of each evidence value that I fixed given its parents. And so either in the sampling distribution or in the weights, every term appears exactly once. And that means that if I take a weighted sampling distribution here, I get all of those terms in the Bayes net appearing on one side or the other. So what does that mean? It means we have a bunch of samples with weights, and when I tally things up, each sample counts in proportion to its weight. Okay. All right. Any questions about that? We'll do an overview, and then we'll look at something a little bit different. Okay, so let's think about likelihood weighting. What was the idea in likelihood weighting? The idea in likelihood weighting is if I have certain evidence values, I have certain variables whose value I know for my query. Like I know this test came out negative or something like that, or I know this light is on in the car. It seems silly to generate samples that don't match my evidence because you're just going to reject them. So think about a big network which has a bunch of variables. And let's say the one you know, and there's a bunch of connections between these variables in this network, okay? And let's say we've got some evidence. We'll make it blue. Let's say this node and this node, we happen to know their values. It seems a little crazy if we know that, say, this one takes on value plus and this one takes on value minus. It seems a little crazy to generate samples that don't match that evidence. Why would we do that? We're just going to throw them out. So in likelihood weighting, we would fix these values, and then as we go down the network, the whole rest of the sample would play out in a way that's consistent with the evidence. This is sort of like hypothetical simulation. Hey, imagine what network? Imagine there was a burglary but not an earthquake. What would happen? Let's simulate. So I fix burglary. I fix earthquake. Because why not? We only care about those samples. And then I let the network play out according to its probabilities. That's just simulation. And likelihood works really well when your evidence is at the top, because then everything else that falls out of the network after that conditions on that evidence naturally. However, let's say we had a similar network. We had a bunch of variables, and there's arrows between them. So imagine that's the same network. And now let's say all our evidence is at the bottom. So we know John called and Mary called. And I'd like to know what's the probability of an earthquake. Well, now this isn't quite so good, because as we start simulating, we're like, no burglary, no earthquake. No alarm. Oh, John called, Mary called. That sample, is that going to have high weight or low weight? Right? It's pretty typical up top, because there's usually not a burglary, there's usually not an earthquake. The alarm usually doesn't go off. But then instead of nobody calling me, which would be the typical way that simulation would unfold, I'm like, no, pretend they called. The sample will come off as negative, 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 but they both called. It'll come off with a very small weight, because that's probably not what would have happened if there had been no alarm. And you're going to have lots of samples rolling off the conveyor belt that represent no burglary, no earthquake, no burglary, no earthquake, no burglary, no earthquake. They're all John and Mary calling, because that's how the procedure works. But they all have a very small weight, because that's probably not what would have happened. And so as a result, everything sort of upstream of your evidence doesn't take on values which are typical of scenarios where that evidence has that value. So in likelihood weighting, everything sort of downstream. You simulate the consequences of the evidence, but likelihood weighting doesn't do a very good job of simulating the causes of the evidence. You just sort of like going along simulating a normal day, and then boom, there's your evidence. It's probably pretty inconsistent with what actually has been sampled, and so your samples roll off with a very small weight. So likelihood weighting is good. We take the evidence into account, at least to a certain degree. If nothing else, all the samples do match the evidence, so we don't completely reject anything. And that means more of the samples will reflect the state of the world. But, as we just talked about, likelihood weighting doesn't solve all our problems, because the evidence influences the choice of things that are downstream but not upstream. What we'd really like to do is we'd like to be able to say, I know this variable and I know this variable. So somehow fill out the rest of the network for me in a way that's kind of takes that into account. Like John and Mary are calling. So set that earthquake in a way that is typical, like given that evidence. How do we do that? We don't have a method for that right now. We only know how to sample downward, and usually there won't be an earthquake or a burglary if we do that. So we're going to take a couple-minute break, and then we're going to talk about another technique called Gibbs Sampling, which has its own issues, which we'll get into, but fixes this problem of wanting your samples to take into account the evidence, regardless of where the evidence is placed in the network. Okay, so a couple-minute break, and then we'll take over with Gibbs sampling. Okay, I changed my mind. We're not going to do Gibbs sampling yet. We're going to do some examples. All right. Okay, so first example, we're going to bring back the rain and traffic network. So rain, traffic, we need some probabilities. Something has to live under rain. So we'll say P of R, let's say P of R. Okay, so let's say plus R minus R. What's the probability of rain going to be? Well, let's make probability of rain 0.3. Probability of no rain 0.7. We'll pretend we're not in our perpetual drought. Okay, let's make conditional probability. What lives under T? T is dreaming about the conditional probability of traffic given rain. And so that is, well, there's two probabilities. There's plus traffic minus traffic when there is rain. And then also when there is not rain, there is plus traffic minus traffic. So let's think of some numbers. When it's raining, let's say there's 90% traffic, 10% no traffic. And then when there's no rain, let's say it's reversed. Well, let's say it's 50-50. All right, so we have a Bayes net. What can I do in this Bayes net? I can compute elements of the joint distribution. So probability of rain and traffic, 0.3. That's the probability of rain. And when there's rain, the probability of traffic is 0.9, so it's 0.3 times 0.9. Okay, that's a thing I can do. I could run variable elimination or inference by enumeration, and I could answer questions. Like I could answer, what's the probability of T? Well, I know what the answer looks like. There's some chance of plus T, and there's some chance of minus T. And then there's some numbers, but I don't know what they are. But I could do some compute. Okay, we're not going to do that. Today is sampling day. Instead, what I could do is I could draw some samples from this network and use these samples to compute some quantities. So let's compute probability of plus T in this network according to samples. Well, I sort of need to be able to call like Python's random in order to get fair samples, so I'm just going to make stuff up. So what's my first sample going to be? Well, what's the most likely sample? The most likely sample, which might not happen first, but the most likely sample would be that there's no rain. Okay, so I flip a coin, and 70% of the time it comes up no rain. So my first sample, let's pretend it's no rain. And then at T, I need to pick a value for traffic. So in the no rain case, it's 50-50, whether it will be plus or minus. What would you like? CS188.random, go. Plus traffic. You want traffic. All right. Well, good thing you're in the Bay Area. Okay. All right. So then we draw another one. All right, another one minus R. This one maybe comes out minus traffic. Okay, this one, now there's rain. And now there's traffic. And now there's rain again. And now there's traffic. Okay, and I could keep doing this. All right. So of these four samples that I've just drawn, what is the probability of traffic in these samples? 3/4. Is that the probability in the actual underlying distribution? Probably not. But if instead of 4 it were 4,000 or 4 million, I'd probably get pretty close. That's prior sampling. Prior sampling, I sample each node in the network until I have a complete outcome. I write it down, I write the next one, I write the next one down, and then I answer questions in those samples. Questions about marginals, like what's the probability of T, that have no evidence, that's prior sampling. However, if I want to know what's the probability of rain given traffic, only 3 of these samples matter. This one matters, this one matters, and this one matters. But that second sample represents the kind of strange world where there's no traffic. And if I want to know probability of rain given traffic, those outcomes don't matter to me. So, to do rejection sampling, so I just answered probability of distribution over T using prior sampling, and I got plus T minus T, 3/4, 1/4. Okay, that was with prior sampling. Now I'm going to use rejection sampling to answer distribution over, what did I say it was going to be? R given plus T. All right. I've got 3 samples that are relevant because 1 was rejected. That's not bad. I only rejected 1. That's because my evidence is plus T, which is pretty common in the samples, and it's pretty common in the samples because it's pretty common in the underlying model. Okay. So rejection sampling. reject. Okay, now in the remaining samples, what do I get? Probability of R plus R or minus R. Plus R is 2/3. And minus R is 1/3, because that's the proportion in the samples that survived the rejection process, meaning the samples that matched my evidence. Now, normally it doesn't work that well. But is everybody clear on how I draw the samples? We didn't do likelihood weighting, right? I just drew samples and then rejected ones that don't match my evidence, and I compute quantities on the ones that are left. Draw a lot of samples, you'll get something like the right answer. Okay, any questions on that? Okay. What about likelihood weighting? Let's do that again. Oh, I guess if it's gone, we can just do it on the same slide. All right, let's do this again, except now the network is fire causes alarm. And up here, I need the probability of a fire. And it's either going to be yes fire or no fire. What's the probability of fire? Let's call it 0.01. Probability of no fire, 0.99. All right. Now we need to know the probability of alarm. I still want my other example. I'm sorry, I deleted it. We're going to compare and contrast. There's rain, causes traffic. And remember, we decided that probability of rain was, I don't remember what we said. Plus rain, minus rain, 0.3, 0.7. Now over here we have probability of traffic, given rain. There's the plus R case. There's the minus R case. Plus T, minus T, plus T, minus T. Here this was traffic is 50-50 without rain, but it's 90-10 with rain. Okay, so there's our rain and traffic case. So we didn't do likelihood weighting there, but maybe we should. Let's do likelihood weighting. So remember, we were computing, we have to have a query. So let's say we want to compute the probability of rain given plus traffic. All right, so let's compute it. Now we need to draw some samples. And in this box, I'm going to draw some samples. So what we did before is we drew something like, plus rain plus T minus rain plus T minus rain, minus T, minus rain, plus T. And we said, okay, well, that's fine because this one gets crossed out because it doesn't match my evidence, and I compute probability of R over the remaining samples. In this case, I would get 1/3 probability of rain given traffic. Okay? That's what we did before. Let's do that again. Let's do that again, but with likelihood weighting. Why do we do this with likelihood weighting? We do it with likelihood weighting because we don't like throwing out samples, especially if we're throwing out 99% of our samples. So let's do some likelihood weighting. All right, in likelihood weighting, we say, all right, well, we're going to flip a coin. So we know that T is supposed to take on this value plus. Okay, so we're going to flip a coin at R and see what we get. So let's say we get plus R. Now, normally we'd flip a coin and we'd say T is going to come up plus 90% of the time. We're not going to flip the coin. We're just going to take plus T. And we write down the weight. That thing I did, this whole multiverse of samples, 10% of them just got shaved off because they didn't match what actually happened. So let's do another one. Minus R. Let's say that's the sample at R. Now, normally I would flip a coin at T, and that coin would come up plus or minus 50-50. But you know what? I don't want to waste time rejecting the sample. So I'm going to force the sample to be plus T. You say, wait a minute, it had a 50% chance of not being plus T. And so that beautiful whole sample that I had, half of it is gone because half of it happened in the parallel reality where it came up the wrong way. So this sample has less weight. So now I go to do this. Well, let's do another one. Let's do another, let's say the next sample is plus R plus T. That'll come out with 0.9. So now when I look at these three samples, nothing's been rejected. But sort of one of them didn't make it through quite so well as the others because it doesn't match the evidence very well. So it has a smaller weight. So now what I do when I ask you the distribution over R given T, all the samples are now relevant, but they don't all have the same weight. So what is the mass on plus R? So for plus R, that's this one and this one for a total of 1.8. So here for plus R, I have 1.8. And then for minus R, I just have this one sample, and it doesn't even have as high weight, so 0.5. So as unweighted samples, 2/3 of them are plus R. But the actual weighted distribution here under likelihood weighting is probability of plus R is 1.8 divided by 2.3. Let's call that 0.9. Okay? So you get a different answer because the weights affect how much each sample contributes. And samples that came off the assembly line matching the evidence really well, like plus R, probably you were going to get traffic anyway. They have high weights. And the ones that came off the assembly line, not really looking like your evidence, but what the heck, let's assign the evidence anyway, they're going to have smaller weight because they represent a much smaller chance that you would have gotten the evidence had you let the sampling occur naturally. Okay, questions on that side before we compare and contrast with fire and alarm? Yep. Down here, in likelihood weighting, you are always computing the conditional probability of an event given the evidence that you have fixed. Because every sample looks like your evidence. Yeah, you can't calculate the marginal probability of R from this because you've messed with your samples. They're all evidence matching samples. Now I could run likelihood weighting with no evidence, but then it reduces to prior sampling. Okay? All right, so that's the basic idea, is you go through and instead of just throwing out samples that don't match your evidence, instead what you're going to do is you're going to make them match your evidence, and some will escape with reasonably high weights and others will just get their weights kind of reduced because they don't match the evidence very well. So instead of being rejected when you don't match the evidence, instead you get a smaller weight, and so you have a little bit more signal coming through than if you had just rejected them. That's sort of the success case for likelihood weighting. Before we do Gibbs sampling, I want to motivate it why we're doing Gibbs sampling. We're doing Gibbs sampling because of the failure case of likelihood weighting. So the failure case of likelihood weighting is like fire causes alarm, fire happens only 1% of the time. And what does the alarm do? Well, let's say we have to say what the alarm does in the fire cases and in the no fire cases. Maybe in the fire cases, I need to say the alarm can go off or it can fail to go off. Let's say 90% of the time it goes off and 10% of the time it doesn't work. And when there's no fire, sometimes the alarm goes off anyway and sometimes it doesn't. Let's say 99% of the time it doesn't go off and 1% of the time you get a false alarm. So here's a domain. This domain seems fine. Let's compute some samples. First, what would happen if we did rejection sampling? So first we need a query. So we need a query. How about let's compute the probability of fire, the distribution over fire, given that my alarm went off. How am I going to compute this? Well, I need samples that say plus A. So I could do rejection sampling. Let's do some rejection sampling. Okay, CS188.random. What's the value for F? Remember, it's minus 99% of the time. Minus. All right. Now, given that it's minus, we need to pick a probability for A. This is rejection sampling, so I'm not going to rig A. I'm just going to cross my fingers and hope I get the right thing. What am I probably going to get? I'm probably going to get that the alarm did not go off. Okay, well, this sample is getting rejected because the alarm didn't go off. Let's try another one. What's going to happen at F? Minus. What's going to happen at A? Minus. Okay, reject. Minus. Minus A. Reject. Minus. Minus A. Reject. Okay. There's a fire, and the alarm doesn't go off. Reject. Okay. So we're going to create a whole lot of samples that get rejected. Well, that's no fun. So rejection sampling seems super annoying in this case. Why? Because remember, we reject things unless they happen to match the evidence. And the evidence here is rare because the thing that causes it is rare. Okay? So let's erase all these samples because they are not helpful. Let's do it again, because we thought we had the solution. We thought maybe it's a solution to just rig the alarm, like the alarm's going off, plus A. Okay, now we don't have to, we're not going to do rejection sampling, we're going to do likelihood weighting. I promise every sample will come off with the alarm going off. So let's do it. We're going to flip a coin at F, and we're going to get minus, because you always get minus, right? 99% of the time you get minus. But, hey, plus A. But there's a weight, because if I had picked minus F, what's the chance that I actually would have for reals gotten plus A? 90%. Sorry, if you say minus F, the chance that for reals you would get plus A is only 0.01. So this one only has weight 0.01. Like, it's there, but by its weight, it's basically already a dead sample. Okay, so what's the next one? Minus F. Well, let's rig plus A. You do that for a long time, and you get a whole bunch of samples that look just like that. And you say, all right, well, on the plus side, these are coming out matching my evidence. On the minus side, all those variables upstream, like the samples that I really need are the ones that say plus F. Because those are the samples that are going to come through with high weight. And that makes sense, because when the alarm goes off, there's probably a fire. Okay, maybe someday a plus F sample will pop off. And of course, it'll be a plus A sample as well, because I'm rigging A. Now, what's the weight on this? Well, this plus F won't happen very often, because P of plus F is small. But given that it does happen, the probability of plus A is 90%. And so this sample will have weight 0.9. And so even if I have 20 of these and one of these, let's say that. We got 20 of these and one of these, and then we got to compute our probability distribution over F given plus A. Well, there's the plus F samples, there's the minus F samples. How many plus F samples do I have? 20. But when you weight them, it's just 0.2. And how about minus F? We've only got one sample, but it has weight 0.9. And then, of course, I have to divide these both by 1.1 to make them normalize. Okay? No, I messed that up. I'm just going to say it again, but right, instead of just swapping them. Let's try that again, but right. Minus F. There are 20 minus F comma plus A samples, but in aggregate they only have weight 0.2. Plus F plus A, there's only one sample of that, but in aggregate it has weight 0.9. That's not a probability distribution. I have to normalize by the total weight. But when I do that, I do actually end up with a probability of fire being high given alarm, even though it took a while for me to actually get a sample that looked like that, because my evidence was rare. So likelihood weighting will do the right thing in the end, but let's say I do this again, except fire is now 0.000001. Okay? It'll still work, except now I'm going to get 2 million of the minus Fs, and then finally, maybe I'll get a sample that actually looks like what really happens with the plus A. And when that appears, it'll have such high weight that it'll sort of proportionally do the right thing. But I'm going to waste a lot of time generating stuff upstream of the rare evidence that isn't typical for that evidence. Okay? This is why we need something like Gibbs sampling. All right? Does that make sense? So let's do Gibbs sampling really quickly. In Gibbs sampling, we don't walk through the network from top to bottom, get a sample, and reset. Instead, it's sort of like iterative improvement for CSPs. We're going to start with a complete assignment, and we're going to tweak it a little bit. The end result is going to be that we take into account evidence upstream and downstream, but there's going to be a price. Okay, so here's the procedure. I'll say it in words first. We're going to start with a complete full instantiation. That's an assignment to all variables. For example, random. Or draw a prior sample. Whatever you want. Doesn't matter. Okay, you start with a full instantiation that is consistent with your evidence. You're then going to walk to the variables one at a time, round robin, and leave the evidence fixed, but for every non-evidence variable, you will resample just that variable conditioned on all the rest staying fixed. Okay, we'll walk through an example of that. But you do this for a long time. And so you change this variable and this variable and this variable and this variable, and you do this, and you get the sequence of assignments. If you repeat this sort of infinitely many times, the samples that come off are going to come from the correct distribution, where what that is the probability distribution over all of the non-evidence variables conditioned on the evidence variables. Sort of an amazing property. And the basic idea here is that you're resampling everything, but you're leaving the evidence. And as you resample things, the evidence sort of can influence the things you're resampling through the other variables in all directions. Okay? So let's do an example. All right. So remember, this is going to be in the cloudy causes sprinkler and rain, both of which cause wet grass. And I'd like to know what's the probability of sprinkler given rain. So what I will do is I will fix my evidence. So R has been locked to plus R, just like in likelihood weighting. So here's my Bayes net. R has been locked because it's evidence. And what would I do in likelihood weighting? I'd sort of like walk along the other three variables, flipping coins, assigning each variable given its parents according to my coin flips, except for plus R, which I'd just rig, and I'd get a weight out of that. Here we do something different. We initialize the other variables, call it random, whatever. And then we're going to repeat the following process. We've got a full assignment. We're going to choose a non-evidence variable. So let's say we choose S. I keep the whole rest of my assignment, and I only resample this one variable. Well, I know how to sample a variable given its parent. But here I'm sampling a variable given its parent and its child. And in fact, I'm sampling it given everything else in the network. So we're going to have to think through the math on that. So we're going to resample X from P of X given all other variables. You say, that's in my Bayes net. That is not in your Bayes net. Your Bayes net has P of X given its parents. This is P of X given everything. So we're going to have to compute that. So we're going to draw a sample from P of S given plus C minus W plus R, the whole rest of the network. And so what do we get? We get plus S. Great. We're going to pick the next variable. Maybe that'll be C. We're going to sample a new value of C given all of the other assigned variables. Maybe we get plus C. Great. And we go to W, and we resample W given all of its neighbors, and maybe we get minus W. And we keep doing this. And we get this chain here, okay, of samples. First question. When I did prior sampling, each sample kind of walks through the network and then resets, walk through the network again. So I take sample 1 and I take sample 2. Are sample 1 and sample 2 going to are there going to be correlations between them given the network? Like, no, they're just totally independent walks through the network. Right? How about here? Think about this sample and this sample. Are they going to be correlated? Think you have a big network. You have a huge network. Everything's assigned. You pick variable 712 and you flip a coin. And in the end, what does the network look like compared to before you flipped that variable? It looks exactly the same, except maybe in one place. Okay, so you are no longer drawing independent samples. All right, so the samples are now highly correlated. We're going to have to deal with that. Okay, but you get the sequence of samples. Each one is like a slight variation on the sample that came before it. And if we grab a sample, and then we do this thing for a long time, and we grab another sample, and then we kind of rotate around robin for a while, and we grab another sample. If we wait long enough between samples, then the correlations reduce, and now we're grabbing samples from the joint distribution over all non-evidence variables conditioned on the evidence variables. Okay, so that's great. We now have this Markov chain we run, and we get sample, 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 sample. And if we draw them too close, they just look exactly like each other, but that's actually okay, as long as you run it long enough. That's great. That will give us the ability to draw samples that condition upstream and downstream on our evidence. But we need to do computation to get from one state in the chain to the next. And in particular, we need to be able to compute what is the probability of the currently flipping variable given the whole rest of the network. Well, that sounds bad, right? Isn't this what got us into trouble, was trying to compute conditional probabilities of things given other things? It's not so bad. And the reason it's not so well, that's a lot of math. Okay, let's walk through it. The reason it's not so bad is because the probability distribution over S conditioned on some assignment to the rest. It will look this way for any network. Okay, it's a variable conditioned on an assignment to everything else. Well, that's going to be a ratio. And in the numerator is just an entry of my Bayes net, a probability of all the variables altogether. And the denominator is the exact same thing, but summed over, in this case, S. So I can rewrite that like this. That's a probability of one entry of the joint distribution divided by the sum of a bunch of similar entries in the joint distribution that only differ on the value of S. So if you expand that out, so from here to here, this is P of SCRW is a product of local conditional probabilities, because that's the definition of a joint probability in a Bayes net. But then I look at this and I'm like, this numerator came from the Bayes net formula. The denominator came from the Bayes net formula. And if we look, we see that actually quite a lot of those terms have nothing to do with S. Like P of plus C is in the numerator and the denominator. Right? And P of whatever this is, plus R plus C is in the numerator and the denominator. And in general, almost everything in the network is in the numerator and the denominator in the exact same way, because it doesn't mention this one variable that's changing. And so everything cancels out. And you're left with something really simple. You're left with the following algorithm, which is you want to resample this network. You look at all the terms in the network which mention that variable. These are exactly the things you would join together in variable elimination. You take all the terms that mention that, you assign them, and then you normalize over all the different values of S. And that's it. And the whole rest of the network doesn't matter, because it's going to cancel out, because its contribution to the likelihood function is the same regardless of what you set S to. All right. So almost everything cancels out. You're left with only the conditional probabilities with S. And in general, only the ones with the resampled variables need to be considered. And so it's efficient to resample a single variable. It's not trivial. It's not sitting in the Bayes net like it was for prior rejection sampling. But it's efficient. And you get this nice algorithm that lets you take into account evidence in both directions. There's a couple things I didn't specify yet. Didn't talk about how many samples you need so that your error bars get small. That's the thing you would see in a statistics class. I didn't talk about how far you have to run this Markov chain and Gibbs sampling in order to sort of escape your initial conditions. We didn't talk about that. And we didn't talk about we didn't talk about why it is yet that if you run Gibbs sampling, somehow upstream and downstream evidence is both conditioned. But it should feel plausible, because you lock down your evidence and then you're sampling a bunch of things, and each time you sample a node, you push a little bit of information up, kind of up and down and around the network. So it should make sense that that all gets smeared around the network, but we haven't proven anything about it. Okay, so in summary, we have the following algorithms. We have prior sampling. This is where you walk down the Bayes net from the top so that you can use the conditional probabilities of nodes given just their parents, because that's easy. You walk down the network and you draw a sample. That's great for computing P of a query without evidence. If you have evidence, you do the exact same thing. You walk down the network, but you throw out all of the samples that don't end up matching your evidence. It's a very simple algorithm, but it might be very slow because you're going to reject almost everything. You're going to reject 1 minus the probability of your evidence stuff. We had likelihood weighting, which is also to answer P of Q given some evidence. Here, every sample is relevant, but sometimes they all have so low weight that you didn't really gain much. But sometimes, if the evidence is high enough in the network, your samples actually are all much better, and this can be much faster to converge than rejection sampling. And finally, we have Gibbs sampling, which is a very different style of sampling where you compute a sequence of samples. These have the property that you take into account evidence upstream and downstream in a sort of like naturally unified way. But there were a lot more questions about non-independence of samples and about the actual math you have to do in order to resample a single variable conditioned on the rest of the network. There's a lot more that we're not going to cover. There's actually not a ton more to say about rejection sampling and likelihood weighting, and what little there is to say, we'll say when we see particle filtering with hidden Markov models. But on Gibbs sampling, there's a lot more that we're not going to talk about here. So it does produce samples from probability of query given evidence, but again, only under certain conditions of how long you run it and how often you how you space your samples and so on, depending on what you're doing. Gibbs sampling is a special case of something you might have heard of called Markov chain Monte Carlo. There's a more general category called Metropolis Hastings samplers, which you may have heard about. They're very famous. Gibbs sampling is a special case of that, but it has its own flaws that are addressed by Metropolis Hastings, and you can read about these things. In fact, anytime you see the word Monte Carlo, that usually means sampling. So you could take a look at that stuff. We're not going to cover that here. Okay, that's it for today. We will see you next time. We will talk about taking everything we've done with Bayes nets, merging it with what we were doing with action selection earlier, and start thinking about associating utilities with knowledge and value of information. Yeah, of course.